Yes, great. I will tell you when you are 7 minutes, okay?
Okay, perfect. I'm going to start my timer too. So first of all, it's for me to have been invited to give this review on astro machine learning with along with Marc. This is going to be a galaxy evolution bias view of the challenges and milestones of the topic. And I'm going to focus precisely on the milestones, and Marc in the second part will talk more about the challenges. So very brief introduction about what is deep learning for those of you who don't know.
Helena, I don't see your screen. I don't know if I am the only one, but now I have,
yeah.
it's everything black.
Okay. Let me do this now. Now?
Yes, now I see again the screen.
Okay, sorry about that. But you hear the introduction? Can you hear me?
Yes, yes. Go on.
Okay. Okay. So very brief introduction about what deep learning is. Deep learning is a subset of artificial intelligence and machine learning. And the difference with respect to machine learning is the feature extraction step is automatized. This means that we can save the time and the workload, but also we don't have to assume a priori which are the properties which further correlate inputs with outputs. And when we talk about deep learning, we usually refer about convolutional neural networks, which basically are these kind of cells which are connected to each other by a set of weights. So your input, your output is a function of your input multiplied and convolved by all this set of weights. And if your inputs are labeled and you want to learn your predictions from your labels, this is what we know as supervised deep learning. Why is deep learning so crucial in astronomy? It is because the current and future data surveys, both simulations and real data, are providing us with a huge amount of data. So it's going to be possible to look at this data by hand, and we need automatic methods to do that. For example, it is estimated that to classify all the galaxies which will be observed by Euclid with a galaxy zoo-like approach, 100 years will be needed. So we really have to rely on deep learning methods. Fortunately, deep learning has been successfully applied to a myriad of astronomical tasks with great success, and it's very fast and relatively easy to apply. In addition, since the first paper, which came out in 2015, deep learning has matured a lot, and this is mostly reflected in the fact that this now accepted as a methodology tool. So papers are because you're using learning, but rather deep learning is incorporated as an analysis tool for presenting particular results. And you can also see how the number of papers related to deep learning in astronomy are increasingly exponentially. It's impossible to review all the papers that include deep learning for astronomy in a 20-minute talk. So I present here an incomplete and biased summary of the applications which are very useful. For example, we can divide the applications in three main groups. One would be object detection and segmentation, where the blending and source extraction is included, as you can see here in this image. Then we can have the classification problems, where, for example, we can achieve, classify galaxies according to the Hubble sequence with their morphology. We can also identify rare objects such as galaxy mergers or gravitational lensing or tidal streams. And finally, there are the regression problems, where the output of the model is not a probability or a class, but is rather the quantity that you're interested in, like photometric redshift, cluster masses, or galaxy morphometry. So an example of this. I really like this called Morpheus because it combines object detection, segmentation, and classification. So the input to the model is a 3-band color image. You can have more than one galaxy, and the code automatically segmentates the map, identifying the different sources, and assigns at a pixel level the classification of each pixel being spheroid, disk, background, irregular, or compact, and finally returns an output combine classifications of these probabilities. So in this example, you can see that this is classified as a disk galaxy, although there's some bulge component in the inner part, and that this is a compact. So far, it has been demonstrated that convolutional neural networks are the most accurate way to perform compared with other machine learning algorithms. For example, for morphological classification of galaxies, Chen 2020 presented a very nice comparison comparing the performance of convolutional neural network with other algorithms like logistic regression, supported vector machine, random forest, etc. And you can see that CNNs outperform all the other models, achieving an accuracy of 95%. CNNs have also been demonstrated to be more accurate even than traditional methods, for example, for photometric redshift estimation, where you can see here that error and the scatter is even smaller than traditional ways of deriving photometric redshift as presented in PASCET 2018. So far we are in a way that we can use deep learning in a comfortable way and has demonstrated to be very successful, but there are limitations. In particular, when we are talking about supervised deep learning, we need to rely on a large enough training sample. And these samples sometimes have to be more than 5,000 images. And this set of objects have to be pre-labeled as usually by hand or by other automated algorithms. And most importantly, they have to come from the same domain, being from the same instrument, resolution, or magnitude distribution. So we are trying to understand how can we overcome this issue. I'm going to focus here on transfer learning and simulations, but generative networks are also an alternative. What is transfer learning? We refer to transfer learning to the ability of convolutional neural networks to transfer knowledge between surveys. As I said before, the instrument characteristics such as the PSF, the spatial resolution, or the depth can affect the result of deep learning models trained with images from different samples. So we want to assess how much of the knowledge acquired from one survey can be exported to a new data set. And this is exactly what we wanted to test in this paper in 2018. Yes. Sorry. So in this paper, what we did was we took the models trained and tested with a Sloan digital sky survey images, for which we used 5,000 galaxies to separate between smooth and disk galaxies. And you can see that the models work very well because they maximize the true positive rate and minimize the false positive rate. So we took exactly the same models, and by the model I mean the weights that the model, and apply them to galaxy images coming from the dark energy survey. And the result is the green curve. So you can see that the model performance is much worse because the models are affected by the instrument characteristic. However, we did a small retraining, but instead of starting from random initial weights, we took the weights learned by the Sloan model, and now we only need 500 galaxies instead of 5,000 to achieve a similar performance as for the Sloan model. So the answer to can convolutional neural networks transfer knowledge between surveys is yes, and we have learned that recycling features learned from different surveys can reduce the training sample by 1 order of magnitude. So this is going to be very relevant for doing this kind of analysis with future surveys like Euclid, LSST, etc. However, this refers to the instrument characteristics, but doesn't apply to the different domains such as the magnitude distribution. Models trained with bright galaxies won't be useful for galaxies which are fainter, or the same for deep images, right? Like LSST, which will very deep, and we will have a lot of information in the outskirts of galaxies. The models trained with narrow surveys won't be useful. So what we wanted to do, because we know how to simulate galaxies at high redshift, so we took galaxies with non-morphological classifications and simulated them. We are doing this for a sample of dark energy survey galaxies in a paper which is in preparation right now, led by Vega Ferrero. And you can see here that these are two sets of galaxies. This is a clear spiral and a clear elliptical galaxy. And when we move them to higher redshift or fainted magnitudes, their characteristics almost disappear. So it's very difficult for the human eye to distinguish between these two sets of galaxies. So the question is, can machines recover the features which are hidden to the human eye? And we were extremely surprised because actually they can. We achieve an accuracy of 97% even for the fine magnitudes. And when we test our models on real dark energy survey galaxies, we see that our morphological classification, which separates elliptical and spiral galaxies, correlates extremely well with spectral classification taken from vipers. So this gives us a positive feedback that maybe machines have better view than ourselves. And just a little bit of publicity, this will be the largest morphological catalog up to date, including 27 million galaxies. So please stay tuned because it will come by the end of the year. Another thing that we are as astronomers are very concerned about is errors, right? Because so far traditional neural networks give you as an output only one value, and you don't have any measurement of the reliability and confident estimates. So a way to overcome this issue is to use Bayesian neural networks, where now your output is a function of your input, the weights and the biases, but all of these are probability distributions with a median and a dispersion. So you now, instead of having just one value, you have a probability distribution, and your output is also a probability distribution. And you can even complicate this a little bit more by adding Monte Carlo dropout, as presented in Walmsley 2019, to obtain a somewhat more complex and realistic posterior distribution. This part, so I'm going to give the turn to Marc. Thank you.
Okay, then now we move to Marc.
Okay.
Are you there?
I'm gonna
okay.
Start sharing my screen. I don't know why I cannot start my video. I hope the screen works.
Okay, now you are sharing.
You see my screen? Okay.
Yes.
I'm gonna talk very quickly because we don't have much time, but about what will be the next challenges, or what will be, in my opinion, in our opinion, the future of artificial intelligence. And Helena has been talking about the successes in what we call supervised learning, which means you have a training and you want to classify cats and dogs, for example, but you previously tell the machine what you are looking for. Now, this is not real artificial intelligence. And this is an example of one of the fathers of artificial intelligence or deep learning, who says that if you make the analogy with a cake, supervised learning will be like icing, right? While the full cake is what we call self-supervised learning or unsupervised learning, when you don't impose an a priori knowledge to the networks, to the machines, but you let them find what you're looking for. And this is now what is hitting hard in the field, and we're starting to do what we call self-classification without labels. So remember, Helena told you need to classify images putting a label and saying, okay, you tell first the machine this is a cat, this is a dog, this is a cat, this is a dog, and then the machine learns. Now we are trying to find the way that the machine automatically learns to put things together without knowing a priori what's in these images. And this is just a very recent paper and that shows that very briefly that in fact, without any supervision, just by perturbing the images, the unsupervised learning achieves similar accuracy than the state-of-the-art supervised learning. And this is a huge achievement because you are not imposing any labeling. So what's the impact of this in astronomy? How can you be used for astronomy? So I want to emphasize two main challenges for the near future, which I think where machine learning can indeed have a strong impact. in addition to what it already has in terms of, dealing with large data sets. One of these is, can assist us in making discoveries in this big data era, because what we want to do with these big surveys is discover new things. And second, can we use, or can it help in, understanding or learning new physics, if there is, and again, it will be biased to galaxy evolution. So how do we make discoveries? And one first thing that we have in our data is that it's a multidimensional. It is getting more and more multidimensional. So these ML techniques can help you to visualize your data in a smarter way. This is a very recent paper by Dalia Baron, who is presenting a way of, reducing the dimension of your data space applied to spectra. And you can see that when you have some spectra like that, which have lots of features, and you don't know exactly what's in your data, you can just pass these to what she calls a sequencer. This is a new algorithm, and you can see that the data is ordered. And you see, for example, an emission line here, how you can follow the different redshift of the different spectra, and the emission line which follows the different redshift. So you ordered your data, you visualize your data in a smaller dimensional space, and this will allow you to better understand your data. This is one way to address this issue. Now, another fundamental thing to detect outliers would be, to find unknowns or things that are interesting. And this is typically when new science has been found, is serendipitously, when suddenly a new object is found and you want to understand the properties of this object. Now, this is traditionally done by inspection, but as Helena said, you cannot, with these new data sets, look at everything. So you can use, again, automatic ways to detect outliers. And you think about that, an outlier would be if you know your data has some probability distribution that you ignore, but a complex probability distribution, certainly not Gaussian, and you want to understand if an object has a very low probability of being drawn from this particular data set, it means that it might be an outlier. And you want to look at these objects, because these objects might be fake detections or errors in your pipeline, but it potentially can be, interesting sources. And you can use, in fact, also deep learning to estimate this probability distribution that I'm talking about. So you can use what we call generative models to understand or estimate the PDF of your data in a complex way. And if you estimate your PDF of your data, you can then sample from this PDF and understand and look for anomalous objects or outliers. This is an example of a way of doing this applied to the HSC survey, which is a precursor for LSST, observed with the Subaru telescope, a very deep survey. And what we did is, we apply these deep generative models to estimate the probability distribution of your HSC, so of the data. And then we looked for unlikely objects, so objects which have a very small probability given my data space. And we found, for example, these kind of objects that the machine said these are very weird, in which you see you have a John galaxy with an off-centered blue source here. And we followed these up with Keck, for example, and turned out to be, off-centered AGNs in dwarf galaxies that were found automatically by the machine. Now this is, and we were not the first, they already existed, but the network found these objects as very unlikely and spotted them automatically. So this is a way of illustrating how you can, in a big data, spot or narrow your search into interesting objects. Second thing, I'm going very quickly, unfortunately, but second thing I wanted to question, I think it's challenging, and I think where machine learning can have a potential for us is how can we learn physics from machine learning? And again, from an unsupervised way. Can we extract physical information from the data, just as we do as scientists? So this is a very recent paper, also a very exciting way of doing this, in which people, what they are doing here is, this is a dark matter simulation, an pure N-body simulation, and they try to make the network without supervision extract what's the equation that explains this data. So the network now is going from a set of data into an equation. And you do this going through what we call graph neural networks. So you first build a representation of your data, and then you can extract a symbolic equation that explains this graph. And it turns out that you can, for example, find a new equation that explains the overdensity of dark matters. And this is completely found by a machine. So there's no human supervision here. And I think this is, again, one challenge for these new techniques is trying to, extract information from the data itself. And following to this, so how to extract physics. So we know, and in the field, especially in galaxy evolution, many other fields, as we saw by previous talk, we want to link, simulations in which we have a temporal evolution of the objects to snapshots that we have in observations. And you want to understand the evolution of a given object, you want to link both somehow and extract the information that you know or that you think you are introducing in your simulation and see if it matches your observations and how and where is the physics that fails. And it turns out that machine learning can also help to that by, as Almudena showed in the previous talk, by projecting your simulation into the observational space by including all observational features, and then you can say, okay, can I find some physical information in these feature observations? This will be more a supervised approach, but you can even do that in that particular stage and try to look for physical tracers. For example, this is a nice recent paper too, in which a traditional issue with observations in galaxies is to measure how important is the galaxy merger in the evolution, how many mergers, what's the fraction of the frequency of mergers across time. So this is the merger rate as a function of redshift. And measuring this is challenging because you have projection effects. So you don't know if galaxies are going to merge. You need to assume timescales. You don't know how long it's going to take for the galaxy to merge. So these people, however, in the simulation, you know that. So you can make a training set in which you know exactly what's the truth and how long it's going to take for that galaxy to merge, and train the machine to identify a given time window where galaxies are merging. So the machine will be sensitive to a given now physically defined time. And since you have all the observational effects, you can apply this to data. And they show that, for example, in this paper, that for the first time, morphological and spectroscopic identification of mergers do agree in the merger rate. And it's a nice example on how machine learning combined to simulations, you can link both in this case in a supervised way. But you can also use AI to not only, try to learn and extract some physical information from the data, but also to check if your physics you are inputting in your observation, in your simulations is correct. And so if they live in the same probability distribution of the same space, and if not, where they fail. And this is again in the field of what I was previously saying, in using generative models to estimate probability distributions, complex probability distributions. And so, for example, if you want to say, does my simulation lives in the same probability, or how likely it is that a given galaxy, simulated galaxy, comes from the same observed probability distribution, you can estimate these PDFs with machine learning. This is also a very nice paper coming out today, if you want to check it out, about estimating distributions with ML. And you can see that. So if you estimate these PDFs, you can see how likely it is that a simulated galaxy comes from the observed distribution. And this is what we did in a very recent paper also, in which we try different sets of numerical simulations. So old numerical simulation like the illustrious simulation, and then improvements like the TNG100, these are cosmological simulation, TNG50, and we compare to SDSS what is the likelihood. So now you can estimate a likelihood, a complex, that these simulations come from the same distribution as the Sloan. And you see that as a function of time, we clearly capture the improvement of the simulation. So this is the DSS, and you want the distributions of likelihood to be in the same, following the same distributions. You see that simulations are not yet there. They don't follow exactly the same distributions. So the neural networks know that you are showing a simulated galaxy somehow. However, we can capture the improvement across years. So the first illustrious simulation is clearly off. However, the new simulations are getting closer to SDSS. And this is a completely unsupervised way of measuring how close you are. And then you can look at the outliers here and try to identify why they are wrong. Okay, I'm running out of time, so I will stop here. I will say, summarizing what both Helena and I said, that first, deep supervised learning is still in an infant phase, but it's on its way to maturity. And I think it will most probably be integrated at different levels in many future pipelines for at least, tasks that we have been doing previously with other classical approaches like object classification, object detection and segmentations, and other regressive tasks like photometric redshift estimation and so on. However, this is a very, very fast, moving field, and very exciting. And there's many, many more beyond, just classification. And for example, I just show you some examples of how you can blindly search for interesting objects in large surveys, and how you can use these to compare and extract information from physical simulations. So I encourage you just now a bit of publicity before I end. So we have organized with several colleagues internationally from Johns Hopkins and UCs a bi-weekly ML physics discussions, and we have very nice speakers. So I encourage, it's free to join on Zoom every other week on Wednesdays. So I encourage you to join if you're interested in these. And thank you very much.
Okay, thank you, Marc and Helena. Really very interesting.